How do we make colored light? Well, in the theater world, we use filters, color filters. This is Rosco, and they make, they're a company that makes colored filters. Rosco Lux is a line of their colored filters, and we can stick those colored filters in front of light. Light sources inherently contain a portion of the visible spectrum of color. The color filters are used to subtract out some of the colors of light from the initial light source and allow other colors of light to pass through. Anytime you use a filter, it is a color filter. It is subtracting light, and it is called subtractive color mixing. So anytime I put a filter in front of a light, that's subtractive color mixing. The lighting manufacturers, the lighting filter manufacturers, publish data that shows how much of the light is being subtracted out and how much is being transmitted. So this AP3200 submissive lavender is Apollo is the company that makes this. And what this is saying in terms of this little t for transmission is that 54.7% of the total light that is created by the light source is actually getting through the filter. The rest of that light is being stopped by the filter. And that light that's getting stopped by the filter actually gets turned into heat and stays there with the filter and can eventually burn out a filter. The more saturated a filter is, the lower the transmission is going to be. So this is probably a pretty, I would say this is kind of a lighter filter. It's letting 54% through. We'll look at another one in a minute that lets a lot less than 54% through. Then if we look down here at this transmission data, this is, once again, here is the nanometers, the wavelengths of the different colors, so 300 to 800. And on this side is the percentage of those wavelengths that's getting through. So if I look right here at 550, right here, we're kind of in a yellow-orange color, and about 50% of that wavelength, that 550 wavelength in nanometers, is actually getting through the filter. And the rest of it is being subtracted out. If I look clear down here at this end, at the really low end, there's like no 300 that's coming through this filter. And there probably isn't 300 necessarily even in the light source that we started with. If I look right here at, that's probably about 725, we're getting at 725 nanometers, which is definitely in the red, we're getting almost 100% of the red that we start with in our light source is coming through the filter. So this chart helps me to understand what colors are going to be available in the light that is the result of this filter. The filter subtracted out 50% of this color, and it only subtracted out a tiny amount of this color, which means there's going to be more of this color to reflect off of my object when I shine a light on that object. Now, the source of light, the original source of light, is also going to have an impact on that. So if this is my original source of light, I'm going to have almost 100% of this red that's going to come through. But if this 2800 is the color temperature of my original source of light, I'm going to have almost 100% of this amount come through. So there's just more red available in my initial light source, so there's more red available once I filter that light. So let's go back to our M&Ms with that blue light. So this is the M&Ms under a light source that has an R80 filter in front of it. So that R80 blue filter is subtracting out the other colors, and it's letting a lot of the blue through. So let's look at a chart for what's actually happening on that filter. So we can look at this chart, and it's similar. We've got the wavelengths in nanometers down here, and we've got the percentage of transmission that's coming through. Right here we have a transmission number that says there's only 9% of the initial light that's actually getting through. So 91% of the light that we started with coming out of the light fixture is being absorbed by the filter. Only 9% is actually getting through. And if we look at the filter, it looks like we're getting through about over 60% here at about the 420 nanometer in that kind of bluish, purplish range. If we come here and look in kind of that yellow range right here in the 600, 550, 600 kind of range right there, there's virtually nothing, less than 10%, close to 0% of that light is getting through. That should really explain to us why these M&Ms that look yellow under white light don't look yellow at all here. They look green because there just isn't any yellow light getting through that filter to be able to reflect back to our eyes. It's all being filtered out. So using one of these charts, you should be able to kind of predict the result that you're going to get if you shine light through one of these filters onto an object. You should be able to kind of predict what color is going to come, what color you're actually going to see the object turn into based on the light that's actually getting to the object. It's not a perfect science, that's for sure. There's a variety of reasons why there's a little bit of different wavelengths it's getting through, and we don't know for sure exactly what's in the pigment of an object too. Sometimes that has an impact. But we can make an educated guess and be relatively close many times. So how do we make colored light? We already talked about subtractive color mixing. Now we're going to talk about adding light sources together with different colors to create a new color. So any color created by combining two or more different colored light sources is called additive color mixing. The color is, and this is with two light sources. The color is actually created in your brain, because remember the light waves that pass through one another do so without changing each other. But nonetheless, if I have two light sources shining on an object, the light rays reflect back to our eyes, and those light rays combine, the stimuli from both of those different colors combine in, and my brain actually puts them together and says that makes a new color. And it actually has to be two different light sources. If you just put two different filters in the same light source, you are just subtracting more light than you did with one filter. It's still subtracting light with one filter. But with two different light sources with different colors, then it becomes additive color mixing. And let's look at predicting the results of additive color mixing. Well, red plus green equals yellow, and red plus cyan equals white, complementary colors. Red plus green plus blue, all of the primaries together, equals white. And what does blue plus red equal? Well, hopefully at this point you should be able to guess. Blue light plus red light equals magenta light, or equals our brain receiving the stimuli from the blue light and the stimuli from the red light, and giving us magenta light. Here's another one. Red light plus green light plus blue light equals a white light. Now, it would be closer to white if I sat there and really balanced out the different amounts of red and green and blue. You can get decently close to white. It's not perfect, typically, if you're mixing red, green, and blue. If I want white light, I typically just want a white light source. So there's a no color white light source on the right. Here's another example. The examples I've given you previously are very saturated colors. These are pretty light colors. So there's a light blue on the left plus a light amber on the right. And the results are, on the left is an amber plus blue white versus on the right a no color white. So look at that and see if you can see a difference. It's subtle, but to me, the yellow M&Ms and the blue M&Ms, the color pops out somewhat. it seems like those colors are just a little bit brighter to me. And that would be the reason that you might create white light using two different colors, is that you want to pop out those different colors. So let's apply your knowledge of color and light. What can you do to make a blue dress really stand out? Well, if you use a light source with a blue filter, this provides more blue light to bounce back to your eyes and really makes the color pop. What can you do to make a green dress less green? Use a light source with a magenta filter. The magenta filter filters out the green light and lets the magenta light come through. With less green light shining on the green dress, there is less green light reflected to the eyes. So this is a couple of ways that you can work with color, and using the charts from the filters and using your knowledge of a color wheel of light, you should be able to start to predict if what's going to happen, what you're going to see when you shine a particular color of light on an object. Two last things. What color is used for in lighting design? Well, number one, to light actors' faces. And so oftentimes we can't use colors that are as saturated because we need to make sure that the actors' faces look natural, look normal. And so we end up creating oftentimes using less saturated colors like that light amber and that light blue, because they don't make the face look funny, but they do allow us to pop up the color of a dress that the actress is wearing. So we use color to light actors' faces. We use color to create real or perceived environments. We use color to create mood. We use color to mimic a particular light source, or to create like a candlelight versus a moonlight. We use color to create highlights and shadows. We can use color to bring out colors in costumes and sets. And quite honestly, we can use color for anything else you can think of. And last but not least, here's some websites that you could go to for Roscoe. They make color. GAM is another company that makes color. Apollo makes color, and Lee makes color filters. And they have lots of good information on their websites about the different colors and how those different colors will work. Maybe suggestions for how to use those colors to create different lighting effects, because they're trying to sell more color. So that is the end of this lecture on how color and light affects objects.